right, so you may recall from when we started differential calculus, in the very beginning, it can be a lot. You know, you're dealing with all of these brand new calculus rules, which are really just more complicated new algebra, a whole lot of new notation and symbols, a lot of notation and vocabulary that all mean the exact same thing. You know, it can be tough at first to keep it all straight in your head. You know, if you ask for the derivative at a point, that's the same thing as saying what's the slope of the tangent line if we happen to see a graph of a function. And it's the same thing as saying what's the instantaneous rate of change if we know that we're comparing two quantities. But it can take a while to get comfortable and to find that moment where everything clicks together and then it all makes sense. Now we're going to start a similar process, unfortunately, with integral calculus. The good news is that the algebra for this, so when we learn all of the integration rules, is really just the reverse of differentiation. Just like addition, subtraction, multiplication, division, we're dealing with an inverse operation. That'll all be in the next chapter. So in differential calculus, the main question that was motivating it was, how can we figure out what the slope of a tangent line is? And the issue was that, you know, we could find the slope of a secant line, but when we bring the 2 points together, our normal algebraic rules break down because we end up with 0 over 0. So how can we use limits in order to help us work out what the slope of the tangent line is? The motivating question with integral calculus all has to do with area. So in this case, we are interested in the area A of this shaded region, which is almost a triangle, but unfortunately, instead of a hypotenuse, we have the curve x squared, and we have no geometrical means of calculating this area exactly. But we could get an approximation. And we could do this by separating it into regions. As we've seen here, we've divided it into 4 equally wide intervals. And from there, we can just draw rectangles rather than, I don't know what you'd call the shape. It's almost a rectangle, but we have a curvy side on top. Okay, so we're going to approximate with rectangles, but there's actually many ways that we could approximate it with rectangles. For example, here we have lower rectangles. These are rectangles which are always connecting to the curve at the lowest point on the interval. So in other words, if we look at the region here from 3/4 to 1, and we look up top, the area where the rectangle would be the lowest is here at the left end point. So that's the lowest part of the curve within the interval from 3/4 to 1. And similarly, from 1/2 to 3/4, it's going to be here at the left end point, and then the same thing over here. I mean, really, since we have an increasing function, all of the rectangles in this case are going to connect at their left end point. So these are lower rectangles, and we see over here that the area, if we were to actually calculate what the area of those 4 rectangles is 0.21875. Okay, cool, but we didn't have to do lower rectangles. In fact, we could have done upper rectangles. It's the exact same thing, except within each interval, we look for the highest point on the curve. So from 3/4 to 1, the highest point is going to be on the right. So we're going to make that rectangle, and then that one, and that one, and then that one. So we end up with 4 rectangles this time. In the first one, we were missing the first rectangle because it ended up with a height of 0, so we didn't draw it. And then we add up their areas, and we get our answer right here. So reasonably, the lower rectangles have a smaller area than the upper rectangles. If we look at the picture, clearly the lower rectangle's area must be less than the initial one we were interested in. Meanwhile, the upper rectangles, their area put together must be more than the area that we're interested in. I guess we could take their average or something like that. And actually, we'll talk about various ways that we could make this approximation better in just a second. But the one I actually want to focus on now is actually just making more rectangles. So right now we know the area is somewhere between 0.2 and we'll call it 0.5, I guess. But you could imagine if we made more rectangles here, each of them would end up being closer to the curve. So our lower rectangles would not have as much space missing, and our upper rectangles would not have as much extra area. So, and here we can see that if we separated the area into 8 subintervals, we get a higher lower bound and a lower upper bound. So now we know that the areas must be somewhere between 0.27 and 0.4 or so. And then over here in the table at the right, we can see, well, even for 10,000 rectangles, we've got the calculations here. And what we see happening is that as we get more and more rectangles, the area of the lower rectangles is getting larger. The area of the upper rectangles is getting smaller. But those two areas are converging towards the same value. They're converging towards the true area, which in this case appears to be, based on what we're seeing over here, appears to be exactly 1/3. Now we don't have a means to directly calculate this yet, but, and this is the connection to limits, we can approximate it by taking more and more and more rectangles. So you could think of that as either the limit, as we see down here, n representing the number of rectangles. So as the number of rectangles tends towards infinity, then the lower area and the upper area are going to equal the actual area. The other way we could have spoken about this would be to say it's the limit as, say, w tends to 0, where w is the width of each of those rectangles. That's equivalent to saying that the number of rectangles is tending towards infinity. Now, before we go on, I just want to make a note that there's lots of other ways that we could calculate the rectangles, and the AP does it differently than the IB, of course. So the IB is going to use lower rectangles. Oh, geez. The IB is going to use lower rectangles and upper rectangles. I'm experimenting with some new hardware over here. I've got a new tablet and pen situation, and it's just going to be sloppy. I don't have time to edit out every single pen mistake that I make. The AP, however, AP is going to use a combination of these three: left-handed rectangles, right-handed rectangles, and midpoint rectangles. So I just want to differentiate between all of these really quickly. So I've got 5 examples coming up here. Each of them are dealing with the same function, x to the 4th minus 3x squared plus 3, going from x equals -1 to x equals +2. Okay, we want to calculate the area underneath that curve. So we see here in the first example, I've drawn lower rectangles, which over here on the left side, they're connecting at the left endpoint because the function is increasing. Over here, they're connecting at the right endpoint of each rectangle because the function is decreasing. Somewhere like over here, it's possible, it's not a guarantee, but it's possible that the function is reaching a minimum like somewhere in the interval for the rectangle. And that's fine. So it could connect literally anywhere along the rectangle. It doesn't need to be in the on one of the endpoints. And this area is always going to be less than the true area. So we have an estimated area here of like 6.1. The actual area is 6.6. Here I've got upper rectangles. It's just same idea, but the opposite. As the function increases, they all connect to the right. As the function decreases, they all connect to the left. Somewhere down here, maybe they're connecting somewhere in the middle. Now what the AP would do is they'd start off with right rectangles and left rectangles. They do kind of what they say they're going to do. The left rectangles always connect at the left endpoint. So here they're below the curve. Here they're above the curve. Depends on whether the function is increasing or decreasing. The upper rectangles are above when the function increases and below it when the function decreases. And then the midpoint rectangle just has the rectangle's height determined by having the curve go through the midpoint of the interval. So the curve goes through the middle of each of these rectangles. And that one's going to have the most accurate estimation out of all of them. So that's got 6.59 compared to 6.6. Our left rectangle is 6.3, right rectangle is 6.9, upper rectangle 7.1, lower rectangle 6.1. So there's lots of different ways to calculate them. For the IB, we're only interested in lower and upper rectangles, which is a pain when we have situations like what I alluded to earlier. So the good news is that the only examples I've ever seen the IB use were always functions that we're strictly increasing or strictly decreasing. So we will never have to worry about one where the function has a local maximum or local minimum. And that'll make any work that they ask us to do a lot easier because you will always know that the endpoint of a rectangle is where the rectangle is going to meet the curve as opposed to some random spot in the middle. That might have seemed like a lot, but I assure you the work associated with this is really not that bad. So let's say we had the curve x to the fourth plus 1, and we wanted to approximate the area underneath it in between x equals 0 and x equals 2. And the problem would tell you how many rectangles to use. So in this example, I'm going to use 5 rectangles. So how wide are each of the 5 rectangles going to be? Well, they're all going to be 2/5, right? So we can mark along here. This will be 2/5, 4/5, 6/5, 8/5, and then 2 is going to be 10/5. So I've got my rectangle widths, and now let's say I wanted to do lower rectangles. So I know that I have 5 rectangles being drawn up here. They're going to all connect to the left endpoints. So each of these rectangles has the same width. That's 2/5. So I'm going to factor that out. And then I just have width times height, width times height, width times height, etc. So what are the heights? The height of the first rectangle is from the left endpoint, x is 0. 0 to the power of 4 plus 1 is 1. Second one, my left endpoint was 2/5 or 0.4. That's the height of the rectangle is therefore 0.4 to the fourth plus 1. And I do the same thing at 0.8, the same thing at 1.2, and the same thing at 1.6. That'll be my final rectangle. I grab a calculator, I pump all that in, and I get an approximation for my area. And that's really all that we're being asked to do right now. We would do the same thing with the upper rectangles, and then we would start at the right endpoints, in which case we would have 0.4, 0.8, 1.2, 1.6, and 2. And we'd skip over 0 in that case. Okay, section B. Literally, all that we need to know is what this notation here tells us. And what it tells you to do is calculate the area underneath this curve in between these two x values. That's all it is. Read out loud, we say, as we note down here, the integral of f of x from a to b, and then with respect to x. Again, we've got that dx showing up there at the end. That really just tells us that we're looking along the x-axis as opposed to along the y-axis. Later on, we'll actually see that. We could actually calculate an area between two various points along the y-axis, something like that. But that's not what we're talking about today. It's known as a Riemann integral. Honestly, most people just call it an integral. So we can now use this fancy notation to ask relatively simple mathematical questions. So in this first one, we've got, okay, the area underneath 2x plus 1 in between 0 and 2. Conveniently, 2x plus 1 is a straight line. So really, this is equivalent to asking, what is the area of this trapezoid? And so you can work that out, right? Half base 1 plus base 2 divided by 2 multiplied by the width. Done. Down below, okay, this is a more complicated looking function, but it ends up just being a semicircle. So we want the area between 0 and 1 underneath that semicircle. Well, that's the area of the circle divided by 4. So nothing to panic about for right now. This fancy notation just means calculate the area. And for right now, at least, we can do that for elementary shapes that we already know, area formulas for. Now things start to get interesting here in section C. Now we're discussing something called anti-differentiation, which, based on the name of it, you may predict is the reverse of differentiation. So we know that we can go from y or f of x and get dy dx or f prime by differentiating. Well, we can move back by anti-differentiating. Okay, we're going to use the notation here can get a little challenging since we're moving back and forth between functions and their derivatives. So what we often use is a capital letter and a lowercase letter to describe relationships between functions a little more clearly. So in this case, if capital F prime equals little f, then we say that the derivative of capital F is little f, and the antiderivative of little f is capital F, or big F, whatever. And for right now, you shouldn't be stressing out about how to actually perform anti-differentiation. Like I said earlier, we're going to cover all that really in the next video, but I just want to look at a few easier ones that I think we ought to be able to kind of reason our way through here. So for example, if we're looking for the antiderivative of x cubed, we're asking ourselves, what function, when we take its derivative, gives me x cubed? Okay, well, we know that when we take x to the fourth, we take its derivative, that's going to get us 4x cubed. So how can we get rid of that 4? Well, we can just take 1/4 of x cubed. All right, so or of x to the fourth, excuse me. So this is the antiderivative of x cubed. Okay, similarly, here we got all the answers now. If I wanted to know the antiderivative for e to the 2x, well, I know that the derivative of e to the 2x is e to the 2x times 2. So therefore, the antiderivative, if I want to get rid of that times 2, I got to multiply by 1/2. So this is its antiderivative. And you can play the same game over there with 1 over the square root of x. Don't worry, we're going to have rules and shortcuts coming up in the next chapter, and they should, for the most part, be pretty easy for you because you already know the differentiation rules. This is just working them all backwards. I just wanted to show you some easy ones, show you that you can work them out already, because the book introduces it at this point. That's basically it. All right, so now what is the connection between anti-differentiation and integrals? Well, I mean, once you really get into this, you kind of just use the two words interchangeably. They're essentially the same thing. Basically, if we've got a function, little f, and we know that it has an antiderivative, big F, then we say that the integral of little f, that is the area underneath the curve of little f in between a and b, this can be calculated by taking the antiderivative of little f, so that's capital F, of b minus capital F of a. Okay, and we call this a definite integral. We're calling it an integral because obviously it's got the integral symbol right there. And it's called a definite integral because we do have endpoints. Later on, we'll discuss what's called an indefinite integral. That's the same thing. It just doesn't have endpoints. And that can be a little weird to think about if you're focused too much on area, like if there's no endpoints, doesn't that mean that you have infinite area? And anyway, that's a topic for another day. Don't worry about it right now. I want to look at just a couple of rules for the definite integral, and hopefully these make sense. The first one says that if we take a definite integral from a to a, meaning like the beginning endpoint is the same as the end endpoint, that has to be equal to 0. And that should make sense. We're asking for the area of a region which has a 0 width. So that should have an area of 0. So hopefully that makes sense. Next, we have the area of the integral from b to a should be equal to the negative of the integral from a to b. So that's like saying, okay, if I want the integral from 4 to 2, that's the same as taking the negative of the integral from 2 to 4. Now, if you just think about it like geometrically, well, it looks like the same shape, whether I'm reading it left to right or right to left. Shouldn't they have the same area? Well, no, and in particular, not according to this rule that we just established, because if we were to switch the endpoints, a and b, then we'd end up switching these two terms, and then that would give us the negative of the original. So in a certain sense, this also means that if you have a region and you're calculating its area from left to right, and you get a positive number, that means that if you're working from right to left, you're actually dealing with negative area, which is another weird thing which we're going to talk about in a future video. Yes, we actually will end up thinking of area as being a signed number, with positive and negative areas being possible, but it's for later. Don't worry about it. The next couple I think are fairly easy. So the third one just says if we're taking the integral from a to b, and then we add that to the integral from b to c, where these two match up, then we can just combine them into a single integral going from a to c. I think that makes some sense. Fourth, just like with differentiation, If we're taking the integral of two functions being added or subtracted together, we can just think of that as taking the integral of one and then adding or subtracting the integral of the other. So that's really convenient. It means that we get to go term by term, just like with differentiation. So that's great. Also very similar to differentiation right here. If we have a constant multiplied by a function, we can just take that constant out and then calculate the integral of the function and then multiply by that constant. So just like when we take the derivative of 3x squared, you don't need to think of it as a product rule. You can just 3 as a constant, do the derivative of x squared, and then multiply by 3. And then the final one here, I wouldn't worry too much about this rule up here. Honestly, this makes much more sense once you just know the rules for integration that we'll see in the next chapter, but we can reason about it geometrically now too. If we've got a constant function, so a horizontal line, and we want to know the area in between 2 points, well, that area is clearly just going to be equal to the height, which is k, multiplied by the base, which if this is a and this is b, then that distance should be b minus a. So that does make sense geometrically. It also ends up making perfect sense once we see more of the rules in the next chapter. So let's just do a couple now. And remember, we're going to use really easy functions for these examples, ones that we can work out the antiderivative of without having to worry about rules. So here we've got the function x squared. And again, we want to find the antiderivative of that. If we take x cubed, differentiate it, we get 3x squared. Therefore, the antiderivative is going to be x cubed, but divided by 3. So that's what we've got right there. So we want to know the area underneath x squared from 0 to 1. In other words, we want to know the integral of x squared from 0 to 1. Using the fundamental theorem of calculus, that's going to be big F of 1 minus big F of 0. It's always top minus bottom. Big F of 1, that's when we put 1 into this function. That's going to get us 1/3. Big F of 0 is when we put 0 into here. It's going to get us 0. 1/3 minus 0 is 1/3. That is the exact area underneath this curve. And this is the problem that we started with way back in the beginning. We saw in the table when there were 10,000 rectangles, we had just 0.33333. I said it looks like it's exactly 1/3. Well, guess what? That area is exactly 1/3. And if we do this one here, we've got square root of x, which is the same as x to the 1/2. If I want to get x to the 1/2, okay, I would take x to the 3/2 and differentiate that. That would get me 3/2 times x to the 1/2. And then to undo the 3/2, we're going to divide by 3/2, which is the same as multiplying by 2/3. So we get, well, they wrote it as 2/3 x times square root of x. I would just say it's 2/3 times x to the 3/2. Same thing. So that's my big F of x in this case. So my area between 1 and 9, that's the integral from 1 to 9 of x to the 1/2. That's going to be equal to this function when x is 9 minus this function when x is 1. We see the calculation for that here, leading us to a final area of 17 1/3. Now remember, this chapter is all this big picture introductory stuff. We're going to have a ton of opportunities to practice problems like this. In fact, chapter 22 is called definite integrals. So we'll be doing definite integrals that whole time. So we'll get used to this idea of capital F of B minus capital F of A. But it's a huge topic within integral calculus. The only other thing that I have to add here is that there's actually a second part to the fundamental theorem of calculus, which is mysteriously not in our textbook, but I think we should still go over it. This one looks a little bit strange, and in my experience, the best advice is don't stress about the fact that there's x's and t's. Just do what I say, and the problem is super, super easy to get right. That said, let's look at it really quickly. So we have capital F of x, and capital of x is equal to the integral from a to x. A is a constant, x is a variable, of a function f of t dt. Therefore, capital F prime of x is equal to little f of x. So this is really the notation that we established earlier. Um, where is it coming from all of this? All right, so let's do like a really easy example together. So let's say that we had big F of x is equal to the integral from a to x, because they always look something like this. Let's get some trig in here. So let's say cosine of t dt. So we want to take the derivative of capital F. I claim that the shortcut answer to this, f prime, capital F prime of x, should be little f, which is this, cosine of x, should be equal to cosine of x. But like shortcut says, put x into this function, call it a day, that's the answer. That may seem unsatisfying. So here's how we can get this the long way. Well, if we actually take the antiderivative of cosine of t, we know that's going to be sine of t, right? Because the derivative of sine is cosine. So then we evaluate sine at the top value, which was x, and then we subtract sine of the lower value, which is a. So we have big f of x equals this function. But then we're going to take the derivative of big F of x, which means that we're going to take the derivative of this. Sine of a is a constant, and we know that the derivative of a constant is 0. So therefore, we're just taking the derivative of sine of x, which we know is cosine of x. Okay, let's just do a couple of these. In my first one, I've got big F is equal to integral from a to x of g squared dg. Okay, my shortcut says that my answer for big F prime should just be the function evaluated at x, so it should just be x squared. We can do it the long way though. First we evaluate this integral. So the antiderivative of g squared, we said that's going to be g cubed divided by 3. That's the antiderivative with respect to g, of course. We're going to take that, but we're going to evaluate it at x, and then subtract when we evaluate it at a. And then we're going to take the derivative of this whole thing. The second term is a constant, so that goes to 0. So we're just taking the derivative of this part here, which gives us 3x squared divided by 3, or just x squared, like I said. So use the shortcut. It's a lot less work. In the second example here, really same idea, except now the x, it's at the bottom. So my shortcut answer is going to be, well, if it's at the bottom, we're just going to throw a negative into it. So this is going to be negative ln of x. Okay, we want to do it the long way. Too bad you don't even know how to do this yet. You have no idea what the antiderivative for ln of t is going to be. We will learn how to do that in the next chapter, but it's a pain to do, and it takes a lot of work. So just use the shortcut. So in this case, we're going to do, question mark of a minus question mark function of x. And then we're going to take the derivatives of both of those. And again, the first term, question mark evaluated at a, that's a constant, so it goes away. Second term, I don't know what the question mark function is, but since I know that the antiderivative of ln of t is question mark, that means that the derivative of question mark is ln. So when we take the derivative of question mark of x, we're going to get ln of x, and then we've got the minus there. All right, finally, what happens when it's not just x? Hopefully something went off inside your head when I said that. When it's not just x, what do we know from differential calculus? What do we need to do when the problem's not just x? We need to use the chain rule, right? So the answer to this one, again, the shortcut here is going to be e to the x squared, but I'm going to end up multiplying this by 2x, which is the derivative of x squared. So the chain rule does come into play. Again, let's do this the long way. The antiderivative of e to the t is just e to the t, so that's really easy. We got e to the x squared minus e to the a, and then we take the derivative of all this. E to the a is a constant, drops out. Derivative of e to the x squared is 2x times e to the x squared. So that's the second half of the fundamental theorem of calculus. That was also part of the option topic previously, so I just wanted to drop that in there just in case it ever comes up. Once again, though, like this chapter is low stress. It's just intro ideas. We're going to use all these ideas and start tying them together with other thoughts and concepts in the next couple of chapters. That's all. Please let me know if you have any questions.